In this video, we are going to be starting to talk about some important concepts that will be applicable to topology. This is a field of math that is very big. It's called abstract algebra. It's very different from the algebra that you probably learn in high school. In high school, you learn how to do things like completing the square, factoring, taking the difference of squares, and expanding that into a factored form. But in the algebra that we're doing today, we're going to be going in a completely different direction. We are studying what mathematicians actually call algebra, more formally referred to as abstract algebra. Okay, and we'll see, not today, but in future sessions, why this algebra is so important. And actually, in our next session, we're going to bring up this idea again when we talk about things like the fundamental group of a space. Okay. So algebra is the study of mathematical structure. What this means to mathematicians is that we're looking at things that involve operations, sets, and functions between the sets. And the reason why this is important is because we want to categorize these structures that appear most frequently. If we can do that, then one might hope that that would allow us to be able to spot those structures more easily and then infer some things about them because they have common elements. So to suggest why this type of approach may be very natural to think about in terms of math, I'm going to look a little bit at our sets that we know very well now, n, z, q, and r. If we start off with n, the most familiar operation that we have is addition. N has an element 0, and it has a very special property. This 0, when you add it to anything, it doesn't change that element. There's a problem with n, which is that subtraction, which is known as the inverse of addition, it doesn't work, right? I can do 3 minus 2, but 2 minus 3 doesn't work, right? This thing is not in my set n. And so I have to expand n a little bit. I have to add in some negative integers. But now, when I add in those negative integers, all of a sudden I can handle that operation of subtraction. The 0 does the exact same thing here, but we also have the additional requirement now that every element z has an inverse. And this is the property that makes the inverse work, right? You just add it to any other element, and once you do that addition, you get back 0. So 0 is already playing a very important role here. We actually call 0 an identity element. And it's an identity element because when you apply the operation with it and any other element, it returns that other element. Now, of course, you may be thinking there are other operations that we can do on n and z. We can do multiplication. There's no problem with multiplication. The only thing is that the identity is going to be a little bit different. It's 1, right? And the reason why, again, why it's an identity is because it fixes whatever element you apply multiplication to with it. So if I do 1 times anything, it gives me the thing that I started off with, and x times 1 gives me not 1, it gives me x. Okay, so now with this out of the way, we can actually go ahead and start thinking about what we can do to invert multiplication. Now, this is again going to be going through the same charade that we did with addition, where now z can't actually handle the inverse of multiplication. In order to do that, we have to expand once more to q. So we're going to expand to q. Remember, q is the set of rational numbers. These are fractions. Okay? And now all of a sudden we can handle division. We actually get our inverses again. So for every element in q, p over q, we can actually find an inverse for it, and it looks like q over p. The reason why it's an inverse is because no matter how I multiply it with my p over q, it always ends up giving me 1 in the end. Okay? And remember, for multiplication, 1 plays the role of the identity element. So let me just highlight that here. Let's just call this the identity. And now I want to make sure that you see the parallel very clearly, right? In both cases, addition and multiplication, we had these two properties. Okay? And the identity was a key property. The operation was another key property. But also the fact that the identity fixes whatever element you have is another key property. So in this sense, addition and multiplication actually work the same way. Now, this is maybe a little bit different from the way you're usually used to thinking about addition and multiplication. Usually, we like to think of multiplication as repeated addition, but what I've just shown here is that the same structure that we have with addition can be found, at least in some sense, with multiplication. Of course, the identity is different, the operation looks different, and in general, the way the operation works on different elements of our sets is going to be different, but we have these common elements, and here's where we start to categorize all these observations. So in general, a set with the three elements of an identity, an operation, and inverses is called a group if it satisfies exactly one more condition, and we'll spell out that condition right now. So if we have now a general set X, we give it an operation, and what this operation does is that it has to take two elements. That's why here I have the product set. It takes two operations, two elements in my set, and then it spits out a third. So to really relate this to a concrete example, we can think of plus as a type of operation. Now here I've drawn it as a little star just to not especially spell it out. I don't want to be talking only about addition or multiplication. I just want to talk about general operations. The plus operation takes in a pair of numbers, right? And then spits out another number. So our definition of a group is going to be a set that has this operation, but it also has to have an identity element. Okay, here I've written it as 1, but I could have well written 0, right? The identity element doesn't have to look like 0 or 1. It could be anything. It could be some squiggly line. Okay, the operation has to be associative. Now, this is something that I didn't mention in the previous cases, but we know well enough that addition and multiplication are both associative. And the last thing that we need for our group is that we need to have unique inverses. So remember how we had inverses for addition, right? So the additive inverse of x was equal to negative x, and the multiplicative inverse of an element z is going to look like 1 over z. Okay. So now with this definition, I'm going to have you in an exercise go through all of these sets with different operations, plus and times, and figure out which one of them are groups. We've actually spelt it out more or less in the previous discussion, but of course we haven't touched R yet. Okay. So today we'll talk, of course, about groups, but we'll focus especially on one sort of group that tends to appear a lot in topology. It will also serve to highlight one of the most basic examples of groups. This is basically everyone's first example of a group. It's called the integers modulo n. So the setup here is that we have an integer n. It has to be greater than 1. And we're going to think about what it's like to divide integers by n. So here I've chosen n to be 3, and I'm going to write down this table here of divisions. So 0 divided by 3 is equal to 0. 1 divided by 3, well, I'm going to go back to elementary basics. I'm going to write them out with remainder because this is the thing that I wanted to point out. So if I keep going, right, I get a little pattern emerging after a little while, and hopefully you will start to see it as I write it all down. And if at any point you're getting lost with the computations, just feel free to pause the video and you'll be able to make sure all of these are correct. So if you were looking at this for the first time, right, you didn't know anything about division, and you were trying to study for a division test, but you didn't know anything about division, and someone just showed you this table, you would want to make note of some patterns. So here are some patterns. The first pattern is that every row has a common element, which is that the remainder is the same. So every row has the same type of remainder. Okay. Now you can make a similar observation for every column, that every column has the same type of quotient, right? Remember the quotient is this element over here, but this is not actually going to be very important for what we're doing today. Actually, this observation here is the basis of our newly formed group. And the point is that there are exactly n possible types of remainders. If we have a general n, here I chose n equals 3, but our remainders were 0, 1, and 2. When we have a general n, the story is similar. It's just that we have up to n minus 1 different types of, well, we have remainders that could be 0, 1, 2, all the way up until n minus 1. Okay? And the remainders, they also cycle. So notice that as I was going down here, as the numbers kept on getting bigger, right, the remainders kept on cycling, 0, 1, 2, 0, 1, 2, 0, 1, 2, 0, 1, 2. And so this is the pattern that you would want to know if you didn't know anything about division and you had to study for a division test last minute. Now, to note the interesting fact that will allow us to get our group structure, because right now I haven't actually defined a group structure yet, we are going to, again, take note of those rows, and we're going to call them now remainder classes, because they basically give us all the information that we need to know about our elements once we divide by this chosen integer n. So each row is an integer class, and the analogy that we want to think about, though, is that if we pick any element from any row, it becomes a sort of representative for that row. It has a property shared by every element in that row, and that property is that it has a remainder between 0 and n minus 1 that is common to every other element in the row. Okay? This analogy actually extends quite far. So let's see why this is important. We're going to pick a representative from the first and second row. So that's this row over here, the class of 0. So let's maybe write that down. So we'll call this the class of 0 because all of these guys have remainder 0. This is going to be the class of 1, and this is the class of 2. And a particularly nice thing is that 1 is in the class of 1, 2 is in the class of 2, and 0 is in the class of 0. So really, there's no way you could mess this up if you were to just use those representatives. Remember, a representative is just a particular element in the row. There's nothing that's going to go wrong if you just use that representative to define the whole class. Okay, so again, we're picking something from row 1, which is the class of 0, and row 2, which is the class of 1. For randomness sake, I'll just pick this guy and this guy. Okay, so 3 and 7. Now, if we add 3 and 7, we get back 10. What is so interesting about this? Well, notice that 3 was in the class of 0, and 7 was in the class of 1. Where does 10 pop up? Well, if we just continue our table, right? I'll remove this thing here that says remainder classes. And I'll write it, 10 ends up going over here. And you will see that it's in the remainder class of 1. So this is the class of 1. Okay. So why is this interesting? Well, now here is like literal addition. It's literal addition of integers. But perhaps we can think about addition of classes. We can sort of draw a separating line here. And I guess on a higher level, what's going on is we're adding two different numbers of different classes. And 0 plus 1, just 0 plus 1 is equal to 1. And if you were seeing this for the first time, you may be inclined to believe, well, maybe this works for every single class. And after a bit of experimentation, you'd realize that you're correct. The representatives actually simulate addition with one small caveat. This caveat is written as follows. The results of our addition in this top bracket here, they have to be restricted mod n. Okay? So what does mod n mean? Well, mod n just means that we have to add or subtract multiples of n to our result until it ends up in this range of 0 to n minus 1. And the reason why this has to be the case is pretty clear with our above example. You can't get a remainder that is not 0, 1, or 2. Right? So in general, if you're dividing by n, you want your remainders to be between 0, 1, all the way up until n minus 1. Okay? So for example, let's add two elements from row 3. Now, what is row 3? In our table here, row 3 is the class of 2. Right? So let me just get this down here. So I chose 5 and 8, right? Now, if we think about what happens in our classes, right? These are both a class of 2, right? So again, 5 is in the class of 2, 8 is in the class of 2. When we add 2 and 2 together, we get 4. When we add 5 and 8 together, we get 13. Now, when we remember what this says here, right? We have to add and subtract n to our result until it ends up in the range 0 to n minus 1. So we have to change this to actually a 1, right? And to do this, we had to minus 3. Now, wouldn't it be amazing if 13 was in the class of 1? Well, check it out. If we just continue the table here, we go 11 over 3, then we go 12 over 3, and look at that. 11 ends up in the class of 1. Okay? Exactly as we predicted. So let me just write that down here again. Okay. Perfect. So now, hopefully I've convinced you that this works. The point is now that we're going to just totally ignore everything that happens in this area here. So we're not going to add the numbers anymore. We're just going to add the classes. And actually, our group structure is going to be made of the classes. So in particular, let's define the group of integers mod n to be the group whose elements are the classes of the integers under division by n. So the operation here is addition, and the identity is the class of integers that are divisible by n. In our example, we wrote the class of 0. Okay, so that was seen over here when we took an element in the class of 0, 3, right? And we noticed that if we added it to any other element in any other class, the class of 1, for example, it gave us something that was in the class of 1. Okay? Now, a class of integers that gives remainder r is actually from now on going to be notated with square brackets. We'll write here the little x. Really, x we could really make it r, right? Oops. Right. But the thing is, sometimes people will choose a different number to go inside this box. R is just a representative of the class. And the reason why I put R here is because usually it's a number between 0 and n minus 1. So for example, up here, we can think of 5, right, is in the class of 2, right? But also 2 is in the class of 2. Right? So that's why we use this notation, because the box number is actually going to indicate what class we're working with. Right? All right. So the group is going to be notated Z with a mod n, with a little subscript n, and I will guide you through an exercise that verifies that this is a group. So it must satisfy the 3 points described in our first definition. Okay, so to close it off, we'll look at a specific example, which is Z6. Now, again, the group itself is composed of these classes, the 0 class, the 1 class, the 2 class, 3, 4, and 5. And this just means the set of all numbers, right, whose remainder is 0 when you divide by 6. Right? The order of our group Z6 is 6, and what this means, the word order, is just the cardinality that we remember from set theory. So literally in the finite case, you just get to count how many things are inside. Okay, so we're actually going to check now that the addition here works, right? So one thing that we would like is that 1 plus 1, when we add the classes, is equal to 2. Remember, now we're working with classes, we're not working with the actual integers that these guys represent. So if a and b are elements in 1, we have to show that whatever we get back has to be an element in the class of 2. So if a and b are elements in the class of 1, we should be able to write them in this way, where we get 6 times some number, but plus 1, and then b can be written the same way, but with a different number c. Right? So C1 and C2 are just integers, and this just says that dividing a and b by 6 will give you a remainder of 1. Then look what happens when we add these two guys together. We get 6c1 plus 1 plus 6c2 plus 1 And if we factor around and play with it a bit, you'll end up getting this. And what does this say? Well, this says that the number a plus b is going to give a remainder of 2 when divided by 6. Okay, so in doing this, we've actually verified that the addition in Z6 behaves exactly as we would like it to. Now let's do a little more complicated example, one that will require us to do that reduction mod n that I was talking about earlier. So we're going to check, for example, that if we add the class of 2 and 5 together, it ends up giving us the class of 7, but the class of 7 is the same thing as the class of 1. Here I, again, reduced 7 by mod n, so I just removed 6 to get to this one over here. So these two actually represent the same class. I could have picked 7, I could have picked 1. The thing that they have in common, though, is that when you divide by 6, it gives you a remainder that is 1. Okay, so now doing the same trick, let A be in 2 and B be in the class of 5. Then we write A and B in the same way, and then we do the addition, right? So if we add A and B together, I get 6C1 plus 2, and then 6C2 plus 5. And then I can group the C1 and C2 together under the 6 using factoring, and then I'm left with a 7. Remember, we have to reduce this mod n, so this is not going to be a good remainder. This is not a remainder. So we have to keep removing multiples of 6 until we end up with that. So that's it. It's not too hard to see that we can pull out another 6. Let me just write explicitly, right? So all this stuff is divisible by 6. And then I can factor even further by writing 6c1 plus c2 plus 1, and then add 1. And now I see that this is the remainder of 1. Right? So whatever elements A and B are, if I know that they are in the class of 2 and the class of 5, then I know that their product has to be something in the class of 1, because when I did the operation here, I got something whose remainder was 1 when you divide it by 6. Okay? So that concludes everything I wanted to say about these groups about integers mod n. In general, right, we can form the group of integers mod n, and the addition in this group will have exactly will behave exactly as the addition on integers. But we have to also mod by n, as we did in this case down here.